All the fun that we just had. So I was very pleased with the sort of new breakdown from this. That I don't know. I guess you guys responded. I don't know if this one was seen as easier than the other one, or perhaps not as out of the blue. Certainly, the last one had some more difficult, perhaps mechanism questions and stuff. But I think that it was pretty good. This should say for reference. Oh yeah, jump down there. But anyway. But you can see, like, clearly, I was really happy with this big cluster in this sort of 60 to 80 range, because I think that if you can get above a 60 on an organic chemistry exam, it's very respectable and something you should be happy about. So I was very happy that there was that many people in that range, and so I think that you guys responded really well, and I was pretty happy to sort of see these scores. So again, I've sort of adjusted a little bit based upon I recognize that this one was a little bit more difficult than this one, and so sort of how you perceive your grade will obviously be a little bit different, right? The same grade that you got on this one, if you get the same grade on this one that you got on that one, then technically you've probably done a little bit worse, right? Because the average is significantly higher now. Everybody seems to be doing significantly better on this one. But I would say in general, most people, as I was going through and sort of looking and putting in the grades, I definitely noticed that there was a number of people that were in the 20s previously that are up in the 50s now. So, I thought that I was very pleased to see it. I think that hopefully you guys that did well are pretty happy. And so I would just say sort of keep it up. I know that there weren't any like grand challenges or whatever on this one. There will be some in the final, so don't get complacent. Keep pushing it, and hopefully we'll have a successful semester. Because again, if we have a similar profile to this than on the final, it'll be nice if I can pass 80 to 90% of this class. And if you guys can do something like this on the final, I think it's possible. So, all right, with that, I'm happy. You guys should be good. All right. So again, yeah, just a reminder, so you'll get them. I'm not sure if Danielle got around to photocopying the exams. I think that she did it yesterday, but I'm not sure. I haven't seen her. She's not around today. But presumably they'll be photocopied and you'll be able to get them back. Again, if you have recitation today, aren't there a couple today? So I'm not quite sure if people that have them today will get them back. You might get them back. But I would say definitely by Friday, the people that have Friday will definitely be able to get them back. So again, just sort of look through them. Obviously, we're human, so there are mistakes. Definitely double check to make sure that specifically, I would go through and make sure there's no adding mistakes. We always double count and stuff like that, but certainly it happens pretty much every exam that there's some add mistakes. So double check to make sure that your grade is right, and let us know ASAP, and that's a quick and easy change. If there's a problem that you don't understand why it was marked completely, if it seems completely right, again, and you don't know why you lost points, talk to your recitation instructor. If it is a mistake where, and again, this does happen, where something's mistakenly marked wrong or points are taken off for something that shouldn't be marked wrong, oftentimes what that's the result of is us giving you back the photocopies. And so we'll have written something down in pen, and you'll sort of look at it and say, what did I do wrong? And it's like, oh, this is actually from us writing down, you forgot this or something like that. So, but certainly, ask us about that anyway, and we'll take a look at it. And again, if it's confirmed that it's definitely a mistake, then it's a quick and no-brainer change. Same extent, if you're sort of concerned, I got 5 points and my friend had a very similar answer and they got 7 points, I want the extra points, I would just please ask. It's certainly in your right to ask for those extra 2 points. But in those events, we will regrade the whole exam. So if there's a question somewhere in between, fill out a regrade request form. And again, the reason that I do that is it's a big class, and unless it's really worth it for you to get those points, like what I don't generally like doing is rewarding the people that are always asking for points on every exam, because a large percentage of people don't ask for the points. And so I think it's sort of unfair to the people that sort of accept their grade and move on when other people are trying to get extra points. So I will certainly look through them, and if there's some great injustice, we will recheck your exam. But again, we'll look at the totality of it because there's a chance that you might have lost points somewhere else. So be sure that you are going to get full points. And so forth. But again, if it's a blatant mistake, just let us know. We won't look at anything else. We'll just correct those. All right, so today we're going to start with crazy Russian hacker. So this just happened to be the quickest video that's going to serve my point. So what we're moving on to in the class now is going to be, we're sort of past reaction synthesis. Certainly there will be a major component of reaction and synthesis on the final exam. So it's worth continuing to sort of think about it, maybe practice it periodically, so that, if you don't lose it, if you don't use it, sometimes you lose it. So you may want to just sort of practice synthesis periodically over the next month, just to sort of stay sharp at it if you worked really hard getting up to speed on synthesis. That way you won't have to invest too much time before the final. But besides that, in terms of new material, we are going to learn a few new reactions, but largely these are going to be based in the context of sort of bio molecules. So really what we're doing now is transitioning from sort of synthetic organic chemistry to sort of biochemistry in a way. So organic chemistry is sort of like chemistry is like, I'm giving a talk on Thursday, and I actually have this as my intro slide because it's at a med school, and it's not going to be a chemistry department, and so I'm trying to make the connection. Sort of organic chemistry in the same way that organic chemistry is like the central science, right? That it sort of bridges particle world that you would think of as physics with the living world of biology, right? Organic chemistry is sort of somewhere within chemistry, right? It's not the atomic world per se, but it's also not the biomacromolecule. So you guys are going to be sort of learning stuff now that's going to sort of transition to biomolecules. So you'll learn about the building blocks of proteins. We're going to learn about the building blocks of nucleic acids. We're going to learn about sugars. So sugars are small molecules. Sugars are critical in terms of lots of different things, both our ability to recognize in our immune system, for example, will often recognize pathogens based upon sugars that the pathogen will have that we won't have. There's actually a really nice story that maybe I'll tell you today. It's based upon my research from grad school that dealt with a specific class of sugars. But again, we will learn, because synthetic chemistry certainly played a role in all of this, and so we will be learning reactions to a certain extent, but largely this will be more in the context of the studying going towards biochemistry. And so today we're going to talk about carbohydrates, and some of you that are here earlier, I was showing a video that was an old professor of mine, T. Ross Kelly at Boston College, and he was on the Ollie G show. He got a lot of press when I was actually in grad school. So there's some funny videos of him out there. But he's also been on like Modern Marvels and stuff and all these other things. So anyways, he's like fantastic educator. He's won tons of teaching awards. And one of the big things that he'll often do is do huge demonstrations. And fortunately, sometimes these demonstrations bordered on whether or not they were safe or not, because he's towards the end of his career and probably has been doing it for forever. But one of the demonstrations within carbohydrates that he did, I'm going to sort of show a video. I'm not going to bring it in. We've actually got the EPA, or someone from the EPA these few days, like checking out stuff. So if something I'm going to be dragging sulfuric acid down into a lab. I probably wouldn't want to do it anyway, but definitely not when people are coming through to sort of inspect about these things. But as you're watching this, sort of make a point about the sort of name carbohydrates. Carbohydrates are just like the name says, it's carbon and hydrates. So if you look at, and we'll discuss this a little bit, it's really broken down into a certain number of carbons, certain number of hydrates, and you can sort of track this name all the way back to before people really understood structures and so forth.
What's up, everybody? Welcome back to my story.
This guy seems to have personality.
Safety shield as well, and I got gloves over there, 5 spoons which are close by, just in case. And in this experiment, we're going to do a very easy chemical reaction. Let's check it out. This experiment, we're going to need sulfuric acid and sugar.
So we would do this in the lab.
Sugar, but I don't think it matters what kind of.
And the people that would be sitting like where you guys are would be like terrified.
Let's get this. First, we're going to put powdered sugar. Then we're going to put sulfuric acid in it. The reaction already starting, so what we're going to do is mix it up.
If you would actually do this. I contemplated it, but I'm not tenured yet. So. Right. So anyway, so that's the general idea behind the experiment. So now if you look at this very lumpy looking like black tarish thing here, that's charcoal, right? Basically, if you sort of watch the video, what's happening is, and you guys learned about this, right? Sulfuric acid does dehydration, right? You treat sulfuric to stuff, it's going to lead to elimination processes, it's going to lead to dehydration processes. And so as you're sort of watching the video, you may also notice that there may be a gas that's involved, or at least you'll hear hissing, right? So you see all that gas that's evolving. That's all probably a certain amount of its water evaporating. So that's what that was, right? It was the water, basically, it's exothermic, you're generating water, the water is being released because it's so hot, because it's an exothermic reaction, and then what you're left with is sort of charcoal. So, I don't know, I thought that was an interesting experiment that really kind of almost proves, and if you think back to when people were initially studying sugars and they gave the name carbohydrates to these, this is probably the type of thing that they would do, right? They would run an experiment, they would break down into something, and that breakdown would be water and carbon, and thus the sort of name carbohydrates that we often refer to as sort of sugars. Okay. So again, if we think about what the structure of sugars are, okay, hopefully my computer doesn't stop, because it just went to a black screen. My computer just died on Sunday, and I had to get it reformatted. I plugged in a zip drive, and it just killed my computer. All right, so hopefully there aren't going to be issues with the video being posted later. So anyway, sugars, carbohydrates. Just like we said, sugars is sort of the name that we'll often give them when we think about carbohydrates. The name we give them is sugars, the sort of name that's perhaps also heard as carbohydrates. Again, it's basically saying the same thing, just different names to them. And again, as we sort of stated, the general structure is of any one, or at least the general molecular formula is going to be sort of C, some number of carbons, and then some number of water atoms. And so, again, sort of general name here sort of comes from hydrated carbons. And so some example of some that we know that are sort of smaller, right? Within these, they can be separated into really two different names. So we've seen these in the past, right? And we can sort of separate them into two groups. On the one hand, what we'll sometimes have is what's called an aldose. Okay, so the aldose again, we'll just sort of show generic stereochemistry there. This would be your aldose. So what you'll have is a sort of carbonyl or an aldehyde at the end. So this would be an aldose. And again, as we'll discuss, there can be sort of repeating units of this unit within there. So just sort of n number of sort of carbohydrates, right? Carbon, water. So you'll have these sort of repeating units within there. And then on the flip side, the other possibility is the same thing, just sort of a linear structure such as that I've drawn, but instead we're just going to put the carbonyl internally, right? And so in this kind of molecule, you could imagine something called molecule like this, where now you have a ketone instead of an aldehyde, and you might guess the sort of name of this is analogous to this, except that it's going to be a ketose. So again, this is the sort of the nomenclature that you'll often hear referring to the two different subclasses of sugars. They can be sort of ketoses, they can be aldoses, and all that this is referring to is that sort of first part of the name. It's going to be whether it's an aldehyde carbonyl within there, or whether it's sort of a ketone within there. Now, just as a refresher, when you guys learned about Fisher projections, it's sort of worth mentioning that sort of Fisher projections, anybody that had the course with me, I certainly talked down the importance to a certain extent of Fisher projections within the sort of broader synthetic chemistry community. But what I also sort of pointed out was that where Fisher projections sort of remain important and where they're used fairly commonly is when we're referring to sort of sugars. It's just a sort of a way that people draw them easier. There's some advantages to sort of drawing them in this way and sort of comparing them, and certainly Fisher himself made a name for himself within sugar chemistry and understanding stereochemistry within them. So just as sort of a refresher again, if you think about a molecule that might be an aldose, for example, standard aldose. In these cases I've shown generic stereochemistry, so it can be either way. But for sort of standard Fisher projection, right, it's going to be this triangle. And again, what this really means is that everything that's on this sort of parallel axis is going, sorry, the horizontal, thank you, axis is going to be coming towards you, right? Right? And you can sort of think about this like a bow tie, right? And then everything that's vertically you just sort of keep as that straight line. So you just take the sort of horizontal and you just make those coming towards you. And again, if you can sort of remember that they're going to come towards you, there's that sort of bow tie rule that you see it as the shape of a bow tie, right? Because this ends up looking like sort of a bow tie. So that could be the way that you could remember these. Now, one of the ways that sort of sugars become a little bit complicated, and one way where the sort of Fisher projections can help us sort of think about sugars, is again, molecules are dynamic systems, right? We've sort of spent a lot of time talking about redrawing molecules in different forms and so forth, and it turns out that sugars generally don't exist as a single sort of linear compound. They often cyclize for various reasons, but oftentimes the better way to draw them, as we'll see, is sort of in a cyclical form. And so we'll look at these a little bit in terms of different ways in which the sugars may look, right? But we start with a sugar, right, that looks something like this. Okay, and I'll just keep going down. This is going to be a little more complicated. I'll just put this OH here. Now, when you have an aldehyde or a carbonyl in a system, you've got a hydroxyl somewhere nearby, it turns out that if that can sort of fold up into a ring system that's either a 5-membered ring or a 6-membered ring, that often will happen. Again, we don't generally think about carbonyls as being perhaps, we think about carbonyls and we don't think about hemiacetals as generally forming. But it turns out that within ring systems, if you can get to a 5 or 6-membered ring, there happens to be some advantages to this process that can sort of help and sort of show how they exist. So in a situation like the molecule that I've shown you here, what's going to end up happening is this is going to form sort of a stable ring. And we'll see you can form 5-membered rings, but the 6-membered ring is generally going to be favored, right? Because we've often seen chair conformations being favored. So if something can sort of wrap around and form a 6-membered ring, generally that's what's going to form. And so as you start thinking about which sort of 6-membered ring is going to form, you can start count from that carbon, right? It's going to be a 6-membered ring. And again, that oxygen is going to be included in that ring, as we'll see. So we've got 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, and then the 6th part of that ring will be an oxygen. So what's going to happen is that this oxygen will make a hemiacetal bond, okay, with the other carbonyl. So what we're going to have is a six-member ring with a hemiacetal within there, okay. Again, one of the ways you could sort of think about drawing this, all right, if we think about what this stereochemistry actually means. All right, so again, right, so that's going to be our sort of carbon count. And again, as we start to think about what this is going to look, as this goes this way, what's going to happen is these molecules, if you sort of wrap around this way, what's going to happen is these are going to come this way. If I sort of draw it, right, appropriately, if I can sort of think about redrawing this, sort of six-member ring. Right? The interesting thing, and one of the reasons why a fissure is sort of a really nice way to draw it, is if you actually think about what this represents as a structure here, what's the geometry between this carbon and this carbon? Sorry, geometry is the wrong word. What is the orientation? And when I'm saying orientation, specifically what I'm referring to is it staggered or is it eclipsed? Right, so these two guys here are eclipsing those two hydroxyls here, which means that these two bonds are also eclipsed. So when you think about it, when you're drawing something in a Fischer projection, really what you're having is a series of eclipsed interactions where the carbons are actually wrapping around. So what this illustrates, even though we have it linearly, right, we're sort of drawing it in a way in which case each bond is whatever 90 degrees from one another, but in actuality, right, it's a much longer bond. And so what's happening here is that even as drawn, it's wrapping around itself. So all of these hydroxyls, when we draw it into a chair, or when we draw it into a cyclic system, all the groups on this side, a whole group, all the groups that are on this side are going to be on one face of that ring. And all the groups on this other side are going to be on the other face of that ring, right? Because simply all we're doing is wrapping this around. These are going to be on one face, these are going to be on the other face. Okay, so as we wrap up this group, and as I sort of draw in this conformation, I'm looking at it, what's happening is the sort of hydroxyls are going to be on one face. So everything, right, so as we wrap up and this sort of goes this way, you can see that the hydroxyls are here, and then everything else is going to follow suit. So the hydroxyls are all going to be on the same face of this molecule. And since I have all the hydroxyls on this face, these three will all be on this same face. And then when we get down here, right, then we'll have to sort of evaluate it a little bit more. And what we'll realize is that when this comes out, it's going to be this proton that's going to come forward, and this one will, in fact, go back. Okay? And so this ends up being the sort of ring structure. Again, now we're bringing them closer into contact with one another, and I think maybe the arrow is the wrong thing to put here. What I'm simply doing is I'm redrawing the molecule from a side view, where this guy's now coming up, right? And if you can sort of redraw this in this way, what you can see is that this molecule resembles this. And there's some really quick methods that you can do that you can maybe learn in your recitation, or maybe your book teaches you, that will allow you to quickly know if I go one way, they'll all be on one side, the other way. But again, if you sort of know at this point and you feel comfortable looking at molecules in terms of 3 dimensions, you can sort of start up here and then recognize that everything else falls in suit. So if you can sort of wrap up and remember what the stereochemistry here is, or even label this as RRS and track it there, then everything else will be on the same face of the molecule. Okay, now, if we draw that molecule and I actually finish doing that mechanism, let's see. When this adds in and you make that hemiacetal, it can really be in one of sort of two directions. And it turns out that when you draw this ring system, what you're going to end up doing is you're going to end up putting it, as sort of shown now, you're going to sort of draw it, as you might imagine, in a sort of chair conformation. Right? It's a six-membered ring. Conformation that's most likely going to adopt is going to be a sort of chair conformation. And again, there's multiple chair conformations that we can draw at this point. We can imagine which of these chair conformations would be more stable. It turns out that in sugar chemistry, it's perhaps a little bit more difficult to predict this. So I'm not going to sort of ask you guys to draw. If you draw the other chair conformation of sugar, I'm not really going to care quite as much, because it turns out that there's complicating factors in sugar chemistry, particularly as it relates to hydrogen bonding, that can help stabilize certain chair conformations over the other. So I don't really care if you end up drawing a different chair conformation. It's not going to be important. So we'll just draw the first one that we see. We're not going to worry about the other chair conformation, but we're going to make a specific point in terms of what the geometry at what is known as the anomeric carbon is. So this is the anomeric carbon. It's the one where you have the hemiacetal, and that's where I really want to focus our attention at this point. So again, just to sort of go through this process that we did in the past, just to sort of think about where everything's going to be. Again, if I draw this compound and I draw it in this way and I want this to be this group here, right, what's going to happen is the proton is going to be going up, right? So proton up, this group down, so that's going to be equatorial. In this case, your hydroxyl is going to be going up. In this case, the hydroxyl is also going to be going up, but at that position it's going to be, at that position it's going to be axial. This position is going to be sort of equatorial. And then what's important to recognize is that you have really two possible, maybe resonance forms is the right way to draw it. But you have two possible protons. Be a little bit more ambiguous. Sometimes in the chairs, right, it's good to draw those. But again, we have stereochemistry here, and we have two possible outcomes. Okay? We have the oxygen in the sort of axial position, and we have the oxygen in the equatorial position. Okay? Now, based upon what you guys have sort of learned in the past, you might assume that this is going to sort of favor the sort of equatorial position, correct? But it turns out that one of the special things about hemiacetals within ring systems is that the geometry, especially in a chair conformation, the geometry and the sort of favorable position of that carbon is actually going to be axial. And there's an interesting reason behind this, and I'm not sure if your book actually discusses this or not, but I think it's sort of worth knowing because it illustrates some of the important factors of thinking about things like sigma star. Right? We've thought about sigma star in the past for SN2 transformations. We thought about sort of alignments of different orbitals, for two eliminations, and the importance of that sigma star in terms of aligning with the carbon proton. It turns out that the sort of axial position is often favored in a chair where you have the hemiacetal. And the reason is that there's a favorable secondary interaction within these structures. And it has to do with the sort of anti-bonding orbital, so the sort of the sigma star of this carbonyl. Now, if you think back to, if we think back to E2 reactions, right? I think E2 is probably a good time to think about this. What you needed for an E2 reaction, right, was that you needed this sort of idea of anti-periplanar nature. Right, so you needed this anti-periplanar nature of these molecules such that when you did a deprotonation, the lone pairs from within that carbon hydrogen could donate in, right, to this sort of sigma star and lead to a leaving group. And that same type of alignment that's necessary for the elimination process is also there at the oxygen as well. So again, if you could imagine this oxygen-carbon bond, you've got in the, sort of on the other side of that is where your sigma star is going to be, exactly 180 degrees. Meanwhile, on this oxygen, you have two sets of lone pairs. One of these is equatorial, and it's heading sort of out towards you guys. We have this other one here, and this is the one that's important for this. And that's going to be sort of axial down. And it turns out that it aligns very nicely with that pi star. And so there's this sort of back bonding ability within there, which you could imagine thinking about as a sort of, I don't know, again, resonance is probably the bad way to explain this, but at least you can sort of, it's not a bad way to explain it, but calling this a resonance form is my point, is probably a bad way to call it. But you can sort of think about it as your ability to sort of delocalize those electrons throughout that system. So it sort of branches out from perhaps what feels comfortable to a certain extent in terms of what we've known, but it's what we sort of use to explain this overall process. So this is what's called, this sort of factor here is what we call the anomeric effect. Okay? And it's a real phenomenon. In fact, in my own research, one of the very first projects that I published in my group, which would be actually a fantastic synthesis question for a final exam, had to do with this discovery that we made. We were actually trying to do something completely different. What we found was that we were interested in studying these reactions of these molecules here called gamma hydroxyphenolates. Now, if you notice these structures, again, we can draw it as the open form where we have carboxylic acid and aldehyde, is certainly that's a form of this. But this is how this molecule more likely exists in closed form for those same reasons. That's just sort of another point to reinforce what you guys learned previously. One of the things that we were interested in doing here is we were trying to do reactions between these molecules and carbonyls. What we were trying to do was something that we thought would lead to a bunch of targets that we were interested in making. But we ended up actually getting something completely different. And that's that we saw this molecule here, so a wacky dioxane coupling process. This is actually an sole undergrad, well, undergrad myself, but the undergrad was the sole person that sort of published it. You'll notice there's this additional stereocenter there, and what that actually is a cyclic sort of ether. Yeah, Felix? What's that? The chair is the same. I've done the equilibration here. Right, because what they can do is go back and forth. So the hemiacetal will undergo effective, it will interconvert between the two diastereomers. So this is the same, yes, this is all the same. This is all the same. The difference is that this carbon, and those can interconvert. Yeah.
Why is one on the left hand or
Anomeric effect. Right. So in this instance, what I'm sort of reinforcing here is that there was additional stereocenter here, and we did some 2D NMR experiments to understand the three-dimensional nature of it, and we actually got crystallographic structure to sort of prove this. But when we got the crystal structure of this, what it ended up being is, what we ended up getting was the crystal structure of something like this. So again, both of the arrow groups were in the same orientation because, again, as you guys sort of learned through chair conformations, these are both equatorial, which is what it would want to be. But this carbonyl here, this carbon-oxygen bond, again, it could have been the carbon-carbon, but it was the carbon-oxygen bond. And it was favored exclusively to this molecule. We didn't see any of the other diastereomer. And again, what we sort of reason this based upon is the fact that you have an anomeric effect that's going to sort of favor this cyclic system being such in the way where that carbon-oxygen bond is sort of anomeric. So this is just an example of where we have seen anomeric effect play out within our own research, but certainly where it had its origins is in sugar chemistry. Margot? Say it again? Why do you need what to do what? Oh, this reaction? Oh, because you eliminate water. Again, I'm not going to go through the mechanism of this. Could be a fun thing to try. Try it on your own. I'll tell you what the intermediate was, and then you can sort of go from there. You need to dehydrate, so you do need acid. You need a really strong acid, triplic acid. But the intermediate is this compound here. So you dehydrate. So the acid is necessary to dehydrate. So you guys can go ahead and try that on your own. It would be a good mechanism problem to try to work through. But again, the idea is, and at least our explanation in the paper is, and you can look back at the paper to sort of figure out whether your answer is right or not. But the sort of overall process we argue and we reason in the paper is due to the sort of thermodynamic nature. A lot of the reactions within here are reversible, and thus it's going to go to the thermodynamically favorable compound, which has the oxygen in the axial position. So again, anomeric effect is something that's sort of real and has its origins within sugar chemistry. I'm really hoping computers. Okay, so six-membered rings. Obviously, if a six-membered ring can form, right, that's going to be what it's going to want to do. Again, we've sort of seen chair conformations will form, but in the same way as I've sort of shown a five-membered ring here, it turns out that five-membered rings will also form. And this will be important where we'll see a lot of five-membered rings, and specifically in like DNA and nucleic acids. The backbones, in addition to the sort of base pairs, the really backbone behind a lot of oligonucleotides, so DNA, RNA, these things are five-membered sugars, cycles. Okay, and so in these cases, six-membered, say this, will often be called a hexose because it makes a six-membered ring. Pentose. Not a hexose. Sorry, I screwed that up. It's a pyranose. Don't worry about this. It's not really that important. But the name for, I think, a five-membered is a little bit more important because you'll start seeing names within nucleic acids that tie to this. So the pyranose isn't really something that comes up that much, and we don't really describe them as that much. But the furanose, we'll see a little bit more. And again, these are just tied back to the sort of names of sort of five and six members. So furan, right, is tetrahydrofuran is this molecule here. Hexahydropyran or 234. Whatever. Yeah, I mean, so those are the sort of base names behind this. In the case of the furanose, you're not going to be able to adopt the chair conformation, so oftentimes we'll draw them in a slightly different way because, again, there's not really any it's not like there's axial and equatorial. So oftentimes it's just better to draw these guys like this. And again, you'll see in nucleic acid chemistry that this is oftentimes how they're drawn. So it's not really clear what they look like in sort of 3 dimensions, and we don't even bother trying to draw them in a way that's 3 dimensions. Certainly can if you want. Generally it puckers into like an envelope. You might read about envelope puckering. So it's not going to be a flat five-member ring. Usually one of the bonds will bend up and it'll make it look like an envelope that's partially open. But anyways, this is how we generally draw furanoses. This is just an example of sort of one of them. Okay, so you'll start seeing those. So in terms of skills for the quiz, when we do have a quiz, or if you want to ask your recitation instructors questions to focus on in your sort of recitations, I think one of the nice things to do at this point would be to really focus on interconverting sugars between, say, for example, Fischer conformations into sort of what the 5-member ring would look like, or sorry, the 5 or 6-member ring would look like. Identify whether it's going to be a hexose, or sorry, excuse me. Identify whether it's going to be a pyranose, right? Can it form a 6-membered ring, or is it more likely going to form a 5-membered ring? And then sort of try to draw it in sort of 3-dimensional orientation, because ultimately in the biological systems that we'll see, they're going to look more, they're certainly going to resemble these sort of structures. All right, so we'll discuss a little bit. Yes? So it'll always form the 6-membered first. It can either form a 6-membered or can form a 5-membered. So if it can form the 6-membered, if there's the option to form the 6-membered, it will form the 6-membered. So generally, the 5-membered are smaller sugars, where you don't have that additional hydroxyl that will be able to bind in. So, for example, this molecule here, what you'll see, right, is that, well, actually, in this case, it could. In this case, I suppose that it could, because this could be there as well. I would assume, so what I would say is that in general with sugars, so I just realized that my argument sort of just fell apart there a little bit, and I'll explain why and hopefully not confuse you guys. But generally, this sort of terminal hydroxyl, we don't really include that in the sugar. That's usually not the one that donates in and makes the rings. So I think what I would do, all right, let me spend a few minutes sort of clarifying this one a little bit. And I'm realizing that I'm not entirely sure why this is even the case, so I apologize. I think Felix asked a very good question that I don't have a great answer for, and I will admit that. But in general, if you have a molecule that has 1, 2, 3, 4, 5, and then say, for example, an OH over here, this could make the 6-membered ring, right? 1, 2, 3, 4, 5, 6, but it won't. You won't. Generally, it'll be this one that will cyclize. And again, I'm not entirely sure why that's the reason. It may have something to do with some favorable interactions over here. I just don't have a good answer for that. But generally, if you now have an additional one within there, that can form. Margaret, you get your hands up. Well, certainly once you've modified it. So what Margot's saying is that in a biological system, you will see it in the 5-member ring because you physically cannot reopen and reclose to form the 6-member ring. But that's in a further downstream modification. I think the question that Felix is asking is, given the opportunity to be a 5 or a 6. And I actually don't have a great answer for that. So maybe the better way to sort of look at it going forward is see if it can form a 5 and see if it can form a 6 and try to draw both of them. Because you're right, actually, now that I'm thinking about it more, I don't think that there's any reason that's, I think, intuitive enough that I would expect you guys to know. So rather than being able to identify a 5 or a 6, maybe just try to draw it in the 5 or try to draw it in the 6, and that's the better skill that I'd say is worth doing. Yeah? 4-member rings are not going to form. No, that's too much strain. I'm sure that there are instances where you could do it. The question is about 4-member rings. 4-member rings are highly, highly, highly strained. So unless there's some enzymatic function that gets it to that way, and then you can't go in a reversible nature, then no. In the cases that we're talking about, right, you have these hemiacetals, and because of the hemiacetal, you can imagine A going back and forth between the two. So yeah, so to answer your question, generally we don't see this oxygen there within the ring, but so recognize that they can form 5-member and 6-member, and maybe just be able to draw the sort of two of them. All right, so any other questions about that? Hopefully that wasn't too confusing. So I just stepped back on, find out whether they can form a 5, find out whether they can form a 6, and then be able to draw the two. Yeah? We can discuss it. We can brainstorm during office hours if you want. We need to get through some material here, but it probably, you know, it's probably, the interesting thing about alcohols, or sorry, about sugars, and specifically alcohols, is that when you have an alcohol, you have this ability to form hydrogen bonding networks. And part of me wonders is if it might have to do with the stability within that hydrogen bond network. And that's why I'm saying be able to determine which chair is so difficult to know because, well, is it the fact that it's axial, wants to be equatorial, is that going to be favored? Or is it going to be the fact that you've got the ability to form new hydrogen bonds when it's in the axial position? And this sort of complicates that sort of nature. So maybe I'll pull back on what I said earlier and just be comfortable interconverting. And don't worry about predicting whether it's going to go to one or predicting whether it's going to go to the other. Know the anomeric effect, certainly, but I would say within that, and even in a situation like this, right, there's two possibilities, and that's going to be difficult to predict as well. Yeah. Yeah, get comfortable. Exactly. So that would be the focus, is being able to convert between the two, both into a 5-membered ring and a 6-membered ring if possible. I think that's the better way to put it. Yeah. 7-membered rings, I've never seen 7-membered rings in sugar, but certainly 7-membered ring systems where you have ethers in them do exist in natural products. And so it's possible that there could be instances where sugars and the formation of the 7-membered ring, followed by subsequent transformations, will lead that way. But you're not going to, given the option to go to a 6-membered ring versus 7-membered ring, you're going to go to a 6-membered ring. And generally, you're going to want to go to the 6-membered ring. It's more stable, and that should make sense to you guys, right? A 6-membered ring is going to be more stable. You can have all the bonds that you want in the sort of right geometry. 5-membered ring has a little bit more strain to it. Not strain, yes, definitely strain. 7-membered ring, though, means that it can likely adopt a 6-membered ring, and so it will do that. Yes?
The chopper is really...
Yeah, I'm not big on naming. I would get comfortable, I would know Furanos specifically. Like, I didn't even know what the name Furanos is. Furanos you hear a little bit more specifically because when they're talking about RNA, DNA, this is where we see a lot of these 5-membered rings. The 6-membered rings are generally when we're talking about polysaccharides. So that's really the big difference. When you see the 6-membered rings, you're generally talking about polysaccharides. When we see 5-membered rings, where you primarily see it is in DNA and RNA as part of the sort of backbone with them. And so that's really the two big areas. Okay? Any more questions? Okay. Okay, so with that, so we'll talk a little bit about chemistry again because, you know, synthesis in general, you know, it's sort of often said within the synthetic chemistry community that there's a feeling out there that synthesis is a sort of a problem solved science, right? And that's partly because in like the 80s, a lot of really good synthetic chemists made a lot of super, super complex natural product targets and convinced everybody that we could generate any molecule that we want. And that's largely true. We can make any molecule that we want as long as that molecule is stable and can exist. But that comes with the caveat of, is there enough resources? Do you have enough money? With an infinite amount of money, with an infinite amount of time, with an infinite amount of manpower, we can make any molecule you want. We really struggle is in efficiency. And one of the big things to sort of note, I think, even now in the synthetic chemistry community, a really big challenge that we really, really struggle with is making polysaccharides, making sugars that are multiple sugars layered on top of one another. These are critical molecules in biological systems. And what I mean by that, specifically when I'm talking about polysaccharides, are instances where you have molecules where you might have, say for example, just an example of one, right, where you might have right, and then on and on and on and on and on. So you have all these connections throughout these molecules where the hemiacetals are filled with all these different things. So there's a lot of these molecules that we would call sort of polysaccharides. And the polysaccharides and the synthesis of polysaccharides is like a huge, huge challenge. So we're going to talk a little bit about amino acids in a little bit. And to sort of put it into perspective, it'll be worth mentioning this later on, coming back to it as well. We're really good at making peptides. We're really good at making amino acids. We can automate these things. We can make them in a way that where you can literally have machines make polypeptides, and we'll discuss that a little bit. Sugar chemistry, you cannot do the same thing. There are brute force efforts. I spent 3 months, I remember in my postdoc, effectively trying to make a molecule that simply had one productive bond, because I was spending all this time protecting all different alcohols, doing fancy chemistry to make sure that the one alcohol that I wanted to react with the other one did all this stuff. So I'm going to talk a little bit about sugar chemistry, but it's important to recognize that synthesis of sugars remains a huge challenge, and so I'm not really going to have sugar synthesis questions for you guys. So don't worry about suddenly me asking a question about the synthesis of a sugar. But there is some interesting chemistry here to learn for sugars. Okay, and the most important has to do with sort of making these bonds. Right? So each of these bonds that I've sort of shown here, certainly there's going to be other alcohols, but every place where you have a sort of, sorry, I'll take that back. The bond would be here. Bond would be sort of, oh my God, that's the worst thing I ever drew ever. Wow, all right, nobody caught me on that. That would have been like a -10 on an exam, right? So these glycosidic linkages right here are really the sort of how all these polysaccharides bind together, okay? And the way that you'll make them is by starting with the sort of hemiacetal that we have, and simply taking them, and again, this is no different than chemistry that we've seen in the past, but it sort of serves, I think, a valuable lesson and a valuable point. If you take sort of hemiacetal and you treat it to an alcohol in the presence of an acid, what's going to happen is, and again, this is actually no different than what you've seen in the past. You're going to be able to get to new acetals, right? Because all these are effectively acetal linkages, yes?
Why do the middle sugar have
Because I screwed it up the first time, and when I corrected it, didn't fully correct it. Yeah, no, it should be in there as well. Yeah, so each of them are going to have these hemiacetals built within the basic scaffold, right? And so as you can imagine, we've seen chemistry like this in the past, right? We saw it within carbonyl chemistry. And when you think about what this really represents, in a way, right, is it's effectively a reaction between a carbonyl and two alcohols, right? It just so happens that usually when we refer to this type of chemistry where a carbonyl condenses with two alcohols, generally what we're referring to is two of the same alcohols, right? But in this case, one of our alcohols is going to be intermolecular, and the other alcohol is going to be one's going to be intramolecular, and the other is going to be intermolecular, and that's how you're going to get these systems like this. So again, it's simply, all it is from a mechanism standpoint is going to be condensation chemistry on carbonyls. So when you see a mechanism like this, you should be able to figure out something that's a rational mechanism that should take you in the sort of right direction. Again, a lot of the other chemistry that the book discusses is chemistry that is just sort of analogous to, again, all of it is really just analogous mostly to sort of carbonyl chemistry. Now, a point within the glycosidic bond formation is that one of the ways that we often will draw the mechanism, and I would suggest doing it this way, instead of going to the open form and trying to do what you did previously, is I would draw in this fashion. If you ever asked to draw a mechanism for a glycosidic bond forming process. Okay, what I would do is I would say that the acid is going to react with the water, with the hydroxyl. What's going to happen is you're going to leave you're sort of going to leave and generate this oxonium intermediate, and then whatever your other alcohol is, it's going to come in. It's going to react with that group. Right, and then what's simply going to happen is you're going to deprotonate it. Right, so The next question might be, what is the stereochemistry going to be? Again, that can be a very difficult question to answer. A lot of work within sugar chemistry is devoted to trying to generate one diastereomer over the other one. From a general thermodynamic standpoint, as you might imagine, what would generally like to form thermodynamically is the anomeric oxygen, so in the anomeric position, as you might expect. But certainly there are other reactions that have been developed that sort of will allow you to generate the axial. And so, again, knowing exactly what's going to form perhaps isn't all that important. You know, again, I don't think this is all that interesting, but I guess it's in the book. You might imagine situations, again, to sort of think about these compounds as sort of mixed aldehydes, right? And so you should probably be able to predict that if you take this molecule and you treat it to sodium borohydride, what would happen? What's that? What? Reduction, right? So it's sodium borohydride reduction, but what's it going to reduce? There's nothing to reduce in here, right? Right, so it's going to reduce the aldehyde form. So if you see sort of a reduction, you just have to recognize that this exists in a tautomeric form with the open carbonyl form. So all that's going to happen at this point is you're going to reduce the carbonyl. And you're going to get to this compound here. So again, a lot of this chemistry, sugar chemistry, is more from back in the day when people were trying to derive.
So with very little treatment, we're usually the open one, but if you apply something to
Yeah, exactly. So we've seen this in the past, right? It's sort of like Le Chatelier's principle, right? Yeah, so when you're sort of at equilibrium, it's very common, and we've seen it in the past, right, where the question was, since you have such little amount in the aldehyde form, why would it react in the aldehyde form? And the point is, like, sort of Le Chatelier's principle, it sort of illustrates the power of Le Chatelier's principle and the fact that chemistry takes place at a time scale and at a sort of a level that we don't generally think. So yes, the aldehyde is going to reduce, and then as the aldehyde is getting reduced, that equilibrium is going to continue to change, and so over time what will happen is you'll be able to reduce it all. Because yeah, you're right, I mean, if it was locked into this conformation, it's probably going to be tough to reduce. So I saw a hand up. Okay. All right, so that's just worth sort of recognizing, I think, that they do exist in this tautomeric form of the aldehyde. So a lot of other chemistry you might even be able to predict, right? So if I gave you guys a question where I said, and this could be the type of exam question that I would ask, where I would try to put two things together, you can imagine a question. And again, so I would probably take sugar chemistry and combine it with carbonyl chemistry, and I could ask you a question and see what you would come up with, right? And so something that I might say is, I had a sugar, right? And the sugar reacted with, say, for example, an amine. A new compound was formed that had X, whatever molecular formula. What you might want to start thinking about is, well, do I know that amine can react with this? No, but let me think about amine reacting with this compound in the carbonyl form. How do amines react with carbonyls? Makes an imine, right? And so what you might imagine in a situation like that you might get to a system like this, and then if you say, okay, well, I think that it's going to be like that, or maybe you might even think that it would shut down and get to a compound like this. Right, so you might be able to predict whether you say this one or the other one, something that would sort of combine the two and that you would have to, again, I just sort of came up with this question off the top of my head. The point being that recognize that these exist as carbonyls, and recognize that a lot of the chemistry that you learned for carbonyl chemistry could also take place here. Maybe probably not Grignard, but yeah. Well, you could just do this, right? I'm not following.
Essentially,
What's my reaction?
You can keep it like that, right? You can just open it and just break that bond. You know, there's no reason to convert it into the fully open extended form, right? Just break the bond, and then you don't have to change anything, right? If there's a question like that, if you're trying to see something through that carbonyl form. Felix, yes? How do I go from here to here? How do I go from here to here? Hemiacetal. Here, sorry, yeah. How do I go from here to here? How do I go from here to here? This one. Oh, no, they're at equilibrium. They're at equilibrium. Yeah, no, that's what I'm saying. It's like so we learned, when we learned about carbonyl chemistry, right, we sort of learned about the fact that you have hydrates, for example, right? So a perfect example, it's all thermodynamically driven, but there is a, right, so if you take, say, for example, an aldehyde, right, and you have water around, there will exist this hydrate, right? There will exist this hydrate. It might be a very, it might be 0.0000001%. But there will be some molecules of the hydrate. But the global equilibrium will favor whichever one is more stable, right? So a great example is chloral, right? So chloral is an aldehyde, right? And chloral, you treat it to water, and it's the hydrate, and it's only the hydrate. Right, so you know, in general, this is favored, but this is an example where this is favored. This is a specific example where that's favored. So it's just based upon thermodynamics. It just so happens that this is an example where this aldehyde is not all that stable because of the electron withdrawing nature nearby. So it would rather exist like this. But in general, aldehydes will want to exist as the aldehyde. So the point is that these are at global equilibrium with one another. And, you know, but it's an equilibrium. It's never going to be 100.0000000 definitive percent of one. Only one molecule among 10 to the 26th, right? There will be a percentage that's very small that will exist in the open form. Same way I would always ask it. So I would expect you to draw the aldehyde, and then again, for the borohydrides, lithium aluminum hydrides, I tell you just think about it as a hydride, H-, and in which way it's just nucleophilic addition. So, all right, so with the last 10 minutes, we'll talk about a couple of the other reactions that you've seen and that we'll see in the book. So again, this is glycosidic bond formation. This is the general, at least mechanistic process behind putting many of them together. But again, as I sort of stated, carbohydrate chemistry can be very, it's a major synthetic challenge. Again, because there's so many hydroxyls, each of those hydroxyls adds to alternative potential products. Okay, so as you might imagine, sort of if we can do reduction chemistry, right, you might imagine that we can also do the reverse process, right? So if we can reduce the aldehyde, aldehydes are also much more prone to be oxidized. So a reduction of an aldehyde is very easy. You can do it with sodium borohydride. An oxidation of an aldehyde is also very easy. So we've seen this in the past, right? Aldehydes you can selectively oxidize an aldehyde. You can't selectively oxidize an aldehyde if there's like water around, right? Because it will just over-oxidize. So that's why like PCC, for example, you need molecular sieves in there to keep any adventitious water out of the reaction. So as you can imagine, there are oxidative procedures as well, in such a way that you won't oxidize necessarily the other components of that, but at the very least you'll oxidize this carbon here. right? And so you can imagine getting into things like carboxylic acid or a carboxylate. Furthermore, you can imagine then condensing that and generating lactones, so cyclizing and making the compounds. But this is something that's worth mentioning. This was actually another process that T. Ross Kelly would actually do an experiment for, so that's called a Tollens reagent. So formally, again, I don't really care about chemistry, like the reactions at this point, far beyond, but there is some classical things to sort of explain here. I feel like at this point in the course, I'm more giving you guys a historical perspective than anything. But so there's this idea behind a Tollens reagent. That's often the way that you can sort of determine whether or not you have an aldehyde in your compound. So it sort of has classical roots, right? If you were an organic chemist back in the 20s, right, you didn't have NMR, you might not have the things that you have nowadays. Certain experiments would lead you to one conclusion over the other. And what you can imagine might have been happening is that they had one class of carbohydrates that wouldn't be oxidized with Tollens reagent, and they had another class of carbohydrates that did. And that was part of probably the classification of, oh, here's this group that reacts with this one, oh, here's this group that reacts with this one. And it turns out that in general it's these sort of aldolases that can sort of undergo this oxidative process. In general, what happens though in this case is that you've got silver at a specific oxidation state, and you bring the silver to silver 0 throughout the process. And so when you have silver 0, it's very obvious. In fact, again, T. Ross Kelly, I show video of this as well. It's like video day today. So we'll let this warm up, and then I'll tell you guys, because this is really cool. Okay, so let me just sort of explain the Tollens reagent, then we'll let the video warm up, and I can sort of tell you guys about this. But again, you can imagine that there might be a situation where you would have an aldehyde. You could sort of determine whether it's an aldehyde or not through this process. And so let me show you guys this, because this is kind of, it becomes very apparent when you see what you observe, how this is the type of experiment that an organic chemist back in the days, when they're still trying to understand things, they can see an obvious protocol here. So hopefully this is a good video.
I'm using tester now as an example now, right? I'm going to give them more water than that. Here's the intensity.
Okay, so basically they mixed everything together, and they see this precipitate.
Next we add oleum on the complex with the silver ions.
Now again, the overall process you're going to see is going to form silver 0. Silver 0 is what we classically think of as silver, so silverware and stuff like that. And so what you're going to see is when this overall process is done, you're effectively going to get a mirror, a silver-like mirror that is the silver 0. And he would do this as a demonstration. So like huge flats.
Watch it in a big shape. Watch what happens. It's happening very quickly. In dark. Put it into the warm water bath. You can already see the mirror beginning to form inside the test.
See, that's the silver 0.
The aldehyde has been oxidized. It is therefore, behaved as a reducing agent, reducing the silver ions in the solution to silver atoms. And we've got the coating of metallic silver on the inside of the test tube. Explosive byproducts can form here, so best defend the confidence quickly as you can.
We were never told that there was explosive byproducts. But anyway, so that's, again, the sort of point that I wanted to make there, that the chemistry that's sort of done, and especially a lot of the chemistry that we're going to be doing now, it's important to recognize the context of it. So it's not like previous chemistry that we've learned where it's like, oh, this is going to be valuable in synthesis. This type of chemistry was literally used to sort of more understand, again, you have two carbohydrates. You classify one as this sort of aldose, and you classify the other as the ketose, and this type of Tollens test was really used to do that. And again, you can see it's such an obvious outcome with that. They say, wow, look at this silver mirror thing, and they could very easily then cluster the two together. So anyways, do you guys do tolerance tests? Oh, cool.
What's the difference between that and sterling?
What's the sterling?
Sterling silver. That is pure silver.
Silver zero? Yeah, I mean, I don't know the I don't know the details of that. All right. So, anyways, I'll probably let you guys go because I gotta hit a train or a flight. But we'll continue on sugar next class. Again, there are these new reactions, but don't worry about these in the context of just try to relate them to previous reactions you've seen. And I think at this point we're sort of more looking at it historically in terms of what the importance is in the broader field. So, okay. Yes.
Remember how we use silver in order to